We're going to move on to second partial derivatives, but I would strongly encourage you, before moving ahead with this material, to make sure the idea of first partial derivatives makes sense, that those examples that we worked through, you understand how we got to each of those solutions, because now we're going to build on that and add some more complexity to that same concept. So with second partial derivatives, it's again the same idea as taking the second derivative of a function, but we're going to have a few different ways that we can take the second derivative. So we already introduced the idea that we can take the first derivative with respect to x, or we can take the first derivative with respect to y. So that notation f sub x means we want the first partial derivative with respect to x. F sub y would mean the first partial derivative with respect to y. When we add on the second derivative, then we add a second subscript letter here. For instance, y. So if we have f sub xy, first we would differentiate with respect to x, and then the second partial derivative would be with respect to y. Similarly, if we had f sub x, we would take the first derivative with respect to x, and the second derivative with respect to x. F sub yx would mean differentiate with respect to y, then differentiate with respect to x, and f sub y would mean differentiate with respect to y, then differentiate with respect to y. So that means there are 4 different types of second partial derivatives we could find, all dependent on the order of the derivatives or the type of derivative we want to take with each step. So in our first example, the first thing that we want to do is, since we're taking f sub xy, the first thing we want to find is the derivative with respect to x, meaning we want to indicate to ourselves which portion of this function have that x variable, and then differentiate with respect to that variable. So in the first term, we would have 2 times y as just constants, since we're differentiating with respect to x, then times the derivative of x squared would be 2x, plus 3 times the derivative of x, which would be 1, y squared, and then the derivative of a constant will again be 0. So we'll get 4xy plus 3y squared. So that's our derivative with respect to x, but our ultimate goal in this problem is to find f sub x sub y. So now what we want to do is take the derivative of this first partial derivative, but now we'll look at it with respect to y. So 4x is just a constant multiple, since we're differentiating with respect to y, and the derivative of y will be 1, plus 3 times the derivative of y squared, which will be 2y, which will give us 4x plus 6y. So again, we need to make sure we keep the order of those derivatives straight, but we essentially just find the first derivative with respect to the first variable listed, then find the derivative of that derivative with respect to the second variable that's listed. So in example 6, we have the same function again, but now we want to find f sub x. So we already have f sub x, the derivative with respect to x, is 4xy plus 3y squared, and now we want to find the second partial derivative of this, or the derivative of this partial derivative with respect to x. So now we'll look at where we have x's occurring. So we'll end up with 4 times the derivative of x is 1 times y plus 3y squared, we're treating as a constant, so that becomes 0, meaning our final result here is 4y. So again, the order of differentiation changes things, or the variable that we're differentiating with respect to can change our results. So in one case, we took a second derivative and got 4x plus 6y. In a second case, we found a different second partial derivative, and we got a result of 4y. So the variables listed in the order that they're listed in will make important differences in those final results. In example 7, we want to find the first derivative with respect to y, and then we'll find the second derivative also with respect to y. So if we're taking the first derivative with respect to y, that means we want the derivative of 6 times the natural log of x over y, where y is the variable part that we're interested in. Or we could rewrite this as 6 times the natural log of x times y to the negative first power. So the derivative with respect to y will be 6 times the natural log of x, since we treat that as just that portion that's a constant multiple. And then we take the derivative of y to the negative first, which will become negative y to the negative second. Or we get negative 6 y to the negative second times the natural log of x. So then what we want for our second derivative is to take the derivative of this result with respect to y. So again, we'll look for which portion of that has that y variable. So this will become negative 6 times the derivative of y to the negative second will become negative 2 y to the negative third times the natural log of x, which will give us 12y to the negative third times the natural log of x, or 12 times the natural log of x, and then rewriting this with a positive exponent, we can move that down to the denominator to write that as over y cubed. In our last example here for second partial derivatives, we have the derivative of x to the sixth plus y cubed to the seventh. So again, we have a composite function where x to the sixth plus y cubed is our interior function. So to start off by finding f sub y, we first need to apply the chain rule. So this becomes 7 times x to the sixth plus y cubed to the sixth power, and then multiply by the derivative of that interior expression. And in this case, we're taking the derivative with respect to y. So x to the sixth will become 0, and we'll differentiate y cubed. So the derivative of y cubed will become 3y squared, or we get 21y squared times x to the sixth plus y cubed to the sixth power. So that's our first partial derivative. Now we want the derivative of f sub y with respect to x. So looking at our result, the only place we have an x variable occurring is again in this interior function. So the result here will be 21y squared, since this is just a constant multiple out front, times the derivative of this composite function, and since we're now differentiating with respect to x, we're looking at that x piece to differentiate. So this will become 21y squared times 6x to the sixth plus y cubed to the fifth. So we haven't updated anything here after starting off that chain rule. But then we'll take the derivative of this expression to get 6x to the fifth plus the derivative of y cubed would be 0. So now just multiplying together and simplifying where we can, 21 times 6 will give us 756, x to the fifth y squared times x to the sixth plus y cubed to the fifth power. So again, whenever something like the chain rule or product rule pops up, we need to start off by following the format that we've introduced in previous sections where we covered derivatives to follow those properties.